In my project, I use trajectory optimization for the swing up of a multi-link carpal system. Then I explore various techniques to analyze the region of attraction of the LQR controller. We have been using the carpal as an example multiple times. It's really easy to modify the carpal system by adding more pendulums on top of each other or directly on the cart itself. This setup is very interesting because it is controllable, except when the pendulums have the same length. We can see that the determinant of the controllability matrix goes to 0 when the two lengths approach the same value. However, if the pendulums have different lengths, the system remains controllable for an unlimited amount of pendulums, just by applying one single control force on the cart. I use direct collocation for the swing up. This method can find good solutions, but if we apply the control input directly, the swing up is unstable. We need to stabilize the trajectory. I use a finite horizon LQR. After the swing up, we need a stabilizer controller. I again use an LQR, this time an infinite horizon, and analyze its region of attraction. I use the cost to go as a Lyapunov function and try to find a sublevel set where the time derivative is negative. I use two different sum of squares programs, the equality constraint formulation and a variation using samples on variety. To use the SOS formulation, I first have to convert all equations to polynomials, substituting trigonometric terms with new variables and leaving the equation of motion in implicit form by adding new constraints. To determine the sublevel set, it's also possible to sample random states and check if V is positive and V dot is negative. Finally, I simulate the system from a range of initial conditions to determine how well the cost to go can approximate the region of attraction. For the carpal with one single pendulum, we can see that the stable region found by simulating is much larger than the cost to go sublevel set. For the carpal with two pendulums, I analyze the effect of the pendulum length on the region of attraction. In this slice of the 6-dimensional space, we can see how the region of attraction gets smaller and rotates as the two pendulum lengths get closer together. I am sure you are wondering what's happening in this situation. Here is a demonstration on how the simple LQR can recover from this crazy initial condition.